Welcome to the Explainer. Today, we're going to tackle a big one, computer science. We're going to break down the core concepts that power literally everything digital in our lives, using the Cambridge IGCSE curriculum as our roadmap.
Have you ever stopped to think about it? I mean, what's actually happening inside that box? It can feel like pure magic, right? Well, it's not. And in this explainer, we're going to build a computer from the ground up, conceptually anyway, starting with the one fundamental secret that makes everything else possible. Let's get into it.
You see, everything, and I mean everything a computer does, is based on a language that's almost shockingly simple. It is the absolute bedrock of our entire digital world.
And here it is, binary. At its most basic level, a computer only understands two states, on or off. That's it. We just represent those two states with a 1 or a 0. Every single photo you take, every song you stream, every word on this screen, it's all just a massive, incredibly long sequence of these 1s and 0s.
So what's so cool about this is how it kind of translates between our world and the computers. We humans, we use the denary system, base 10, 0 through 9. The computer, though, it's all binary, base 2. And then you've got programmers. They often use hexadecimal, base 16, because it's a much cleaner, shorter way to represent those super long strings of 1s and 0s. It's the perfect bridge between human and machine.
And look, this isn't just for number crunching. Thanks to standards like ASCII or Unicode, every single letter, number, and symbol gets its own unique binary code. So when you type hi, the computer doesn't see letters. Nope. It just sees these two specific 8-bit strings of 1s and 0s. It's all just numbers.
Okay, so if binary is the language, who or what is actually doing the talking? Let's peel back the cover and look at the machine parts and the instructions that process all those 1s and 0s.
Think of this as the actual heartbeat of your computer. The central processing unit, or CPU, is in this constant rhythm: fetch, decode, execute. It grabs an instruction, figures out what that instruction means, and then it does it. This is happening billions of times every single second. It's just mind-boggling, really.
Now, that whole fetch, decode, execute cycle is being directed by software. And it helps to think of software in layers, kind of like a cake. At the very bottom, you've got the physical hardware. Sitting right on top of that is the system software, like your operating system. That's the foundation that manages all the hardware. And then, on the top layer, that's where you find application software. That's your web browser, your games, your apps. They're the tools you actually use, and they can't do anything without that system software layer underneath.
All right, so a single computer is an incredible machine. But where does the real magic happen? When it starts talking to other computers. Let's look at how that actually works. When you send an email or load a website, you might imagine your data traveling in one big block. But that's not how it works at all. It's way smarter. The information gets chopped up into these tiny little things called packets. It's like taking a letter, tearing it into 1,000 pieces, sending each piece through the mail separately, sometimes on totally different routes, and then having them all perfectly reassembled on the other side. This whole thing is called packet switching, and it's what makes the internet so fast and resilient.
But of course, this amazing, connected world, well, it's got a dark side. There are all kinds of threats out there. You've got malware, which is just malicious software designed to mess up your computer. Phishing is when criminals try to trick you into giving up your passwords. And then you have things like denial of service attacks, which are basically like creating a digital traffic jam to shut a website down. They're all different ways to try and steal your data or just cause chaos.
So how do we fight back? Well, we build layers of defense. Think of it like a digital fortress. Authentication. That's your password or your fingerprint. That's the key to the front gate. Firewalls. They're the high walls, constantly watching for anything suspicious trying to get in. And encryption. That's the secret code. Even if someone manages to break in and steal something, all they get is a bunch of scrambled nonsense they can't read.
Okay, we've got our computer, it's connected, and it's secure. Now for the fun part. How do we actually tell it what to do? How do we teach it to solve problems for us? It all begins with something called an algorithm. And don't let the word scare you. It's just a recipe, a set of step-by-step instructions to get something done. This stuff you see here, pseudocode, it's like the rough draft a programmer writes out to plan the logic before they even touch a real programming language.
But for an algorithm to work, it needs ingredients. It needs data, and lots of it. That's where databases come in. Forget dusty old libraries. Think of a massive, perfectly organized digital warehouse where a computer can find any piece of information it needs in a split second.
And this is where it gets really fundamental. Every single complex decision a computer makes, it all boils down to simple true or false questions. This is called Boolean logic. It uses these tiny little circuits called logic gates, like this AND gate here. All this one does is ask, are both input A and input B true? If the answer is yes, it outputs a 1, or true. If not, it's a 0, or false. Every single thing a computer does is built on millions of these simple yes or no decisions.
So, we have binary. We have CPUs, networks, algorithms, and logic gates. We have all the fundamental building blocks. So, where is all this taking us?
It leads right here, to the cutting edge. All those buzzwords you hear about, artificial intelligence, robotics, machine learning, they aren't some separate magical thing. They are built directly on top of every single principle we've just talked about.
I mean, let's take artificial intelligence. It feels like magic, doesn't it? But it's not. It's just a brilliant combination of all these core ideas. AI systems use massive databases to get their data, they use Boolean logic to reason about it, and they run on incredibly complex algorithms that let them learn and adapt. The foundation is exactly what we've been exploring.
And really, that's the whole point. Understanding these building blocks from a simple 1 and 0 all the way up to a learning algorithm, it's not just some academic exercise. It's like learning the fundamental language of our modern world. And once you know the language, well, that's the first step to building the future yourself.